Nitric acid acts upon copper. That's been the theme at the beginning of the year, and throughout your first couple of labs, we've been working with copper compounds or else copper metal and solutions of copper. This podcast is to take copper another step and to help teach you how to balance reactions that are not easily balanced simply by trial and error of inspection. So in this example, when we take copper metal and react it with nitric acid, notice how I've written the hydrogen ion and the nitrate ion as ions because nitric acid is strong. Those are the reactants, and now we have to remember and think back to the demonstrations in the lab that you've just finished doing to figure out what are the products formed. So might be a good idea for you to pause the podcast and try to write the products and then come back. I'll do that several times throughout the podcast. So pause, write them, check to see how you do. Copper plus 2 ions are definitely formed. The gas that's formed, what you see with your eyes is actually a brown colored gas, but the gas that's initially formed is nitrogen monoxide. Actually, that gas is colorless, but it quickly reacts with the oxygen in the air, and so what you immediately see being formed is a visual brown colored gas, which is actually NO2, okay? These are the two things that we do see in solution. We know that there is water present, but these are the changes that are going on. Now, in order to balance this equation, a couple of things that you know right off the bat is that you don't see hydrogen on the product side yet. When we balance an oxidation reduction reaction, that is not a simple one, but one that is much more complex like this one, there are a series of steps that we follow, and those are outlined on the next page. The very first step of this process is to identify what is oxidized and what is reduced. So you want to be sure that you know how to figure out the oxidation numbers. So pause for just a moment and figure out the oxidation numbers of all of the reactants and all of the products. All right, the oxidation numbers of both the reactants and products are summarized below. Copper is 0 to begin with because it's in its elemental state, and it is converted to copper as a +2 charge. My question to you, is that oxidized or reduced? Another one that looks like it has changed is nitrogen, going from +5, whoops, I left out an equal sign, that should be equals -1, there we go. Nitrogen goes from +5 to +2. In every redox reaction, something must be oxidized and something else must be reduced. You can't have loss of electrons without something else gaining electrons. There must be both, or you've done something wrong. In this case, we already have something oxidized and what is reduced. And since hydrogen gas is not formed, we can assume that the hydrogen, wherever it is also unchanged in the reaction. So both the hydrogen and the oxygen are not involved in the transfer of electrons. Where we go from here is what I want to show you, the list of steps. So the first step, as you can see from these details, is to figure out the oxidation numbers and then to identify what is oxidized and what is reduced. So you're going to list the symbol of the element oxidized and the symbol of the element that is reduced. So if we go back to the slide, which element is oxidized? Copper is oxidized. And which element is reduced? Nitrogen. So now we know what is oxidized and what is reduced. If we go back to the second step, we're going to balance what is called the oxidation and reduction half reactions. And there's a series of steps that we're going to go through. So I'm going to set it up and show you how we do that. So as indicated, first of all, we want to list the element that's oxidized or reduced. And so I've done this on the first slide. For the oxidation, copper is oxidized. The next step is to balance the oxygen atoms by adding water. Well, in this case, there is no oxygen to balance, so we don't have to do that step. In the next step, it adds, we need to balance the hydrogens, but again, there is no hydrogen, so we don't have to do step C. The fourth step is to add electrons to balance the charge. Well, I can see that the total charge on the reactant side is neutral, on the product side is +2, and so in order to balance the electrons, I need to add 2 electrons to the product side, so net, the total charge on the product side equals the total charge on the reactant side. If we do that same process for the reduction half reaction, we start with the element that is oxidized, and that element is nitrogen. But since the nitrogen was in the form of a nitrate ion, we write the entire ion. And on the product side, we write the formula of the product form that contains the nitrogen that is reduced. So if we go back to the steps, the next step, because the nitrogens are indeed balanced, notice that the number of nitrogens on both sides of the reactant and product side are the same. If they were not, then we would put a coefficient in front of either the reactant side or the product side. Since that's not the case, we don't have to use a coefficient to start and balance the nitrogens. The second step is to balance the oxygens by adding water to the appropriate side. Since there are 3 oxygens on the reactant side and only 1 oxygen on the product side, I'm going to add 2 waters to the product side. Most of the reactions that we deal with this year are going to take place under aqueous conditions, so adding water to the reactant or product side is quite reasonable. So now our oxygens are balanced on both sides. There are 3 oxygens on both reactant and product. The next step is to balance the hydrogens. How do you balance the hydrogens? You add hydrogen ions, because most redox reactions take place under either acidic or basic conditions. So you're going to balance the hydrogens by adding hydrogen ion to the appropriate side. Since there are 4 hydrogen atoms on the product side, I'm going to put a coefficient of 4 in front of the hydrogen ion on the reactant side. So now we have conservation of elements. All of the nitrogen and oxygen and hydrogen atoms are balanced. And we're left with the last step, which is to balance the charge. 2 things to notice. The total charge of all of the ions on the reactant side equals what? Well, it looks like +3 to me. On the product side, looks like neutral. You want, since this is a reduction, isn't reduction a gain of electrons? Yes, it is. Oxidation is loss of electrons, so the electrons are on the proper side for the copper oxidation. In this case of reduction, I need to add 3 electrons to the reactant side, and now we have a half reaction equation where we have conservation of elements and we have conservation of charge. In this example, coincidentally, the total charge on both sides is neutral. That's not always the case. Sometimes the charge on both sides is a positive value or a negative value, but the important thing is that you have conservation of charge. The total charge on the product and reactant sides are the same. If we go back to our list of steps, now we're ready to do the third step in the reaction, which is to ensure that the electrons lost must always equal the electrons gained. Well, you remember the idea of common multiple. In this case, which is a good example, you see that there are 2 electrons lost by the copper and there are 3 electrons gained by the nitrogen. One thing I want to point out, and this is a good check, 3 electrons were gained. If you recall, the oxidation number on nitrogen was +5, was it not? And what's the oxidation number of the nitrogen on the product side? +2. That checks out with our 3 electrons gained, since the oxidation number changed by a factor of 3. That's a good cross check. If you miss that, you might get bogged down with poor accounting of details. Accounting and making sure you've counted atoms and counted electrons is a common mistake made. All right, so moving forward, we're going to balance electrons. What we're going to have to do in order to do that is multiply both equations by some value so that the electrons lost and gained equal. So now we have to multiply this equation by 3 and the second equation by 2. What I'm going to do on the next slide is show you both half reactions with the electrons lost and the electrons gained equal. All right, so now we have 6 electrons lost by the 3 copper atoms, and we have 6 electrons gained by 2 different nitrate ions. And so now it's kind of like adding up polynomials. We'll combine and cancel any like terms. And as you can see from this, there's only 2 things that cancel. In this case, 6 electrons. When we add them all up, we've got 3 copper plus 2 nitrate ions plus 8 hydrogen ions yield 3 copper ions plus 2 NO plus 4 waters. So the electrons lost and the electrons gained have been canceled out, and you're left with what is called the overall ionic equation. Now imagine if you tried to balance this as we did in introductory chemistry by trial and error. With all these coefficients, and this is an easy one, by the way, it would take you forever to get it done. Nearly impossible. So let's go back to the list here. We combine the half reactions. We're finished with number 4. If the reaction is done under basic conditions, there's one more step to do. Okay? And so I'll do another example, and I'll ask you to give it a try and see how you do, and I'll give you the final answer at the end of this podcast. But before I do that, I want to call attention to something as it relates to your lab. Your lab asks you to do a little calculation to figure out how much nitric acid to use for the brass sample of copper, assuming that you had pure copper. Many of you had a variety of answers in your calculation. Perhaps the coefficients in this balanced equation might help you with that process. What do you need more of, the hydrogen ions or the nitrite ions, for this reaction to occur? Probably is easy to see from this equation. Okay. All right, so here we have an example of an equation that has sodium hypochlorite, active ingredient in bleach, working with manganese dioxide or manganese Roman numeral 4 oxide, and a redox reaction occurs. The first thing that I want to suggest that you do in this case, since it's under aqueous conditions, is to get rid of any spectator ion that you see. And hopefully, if you pause the podcast, you'll be able to recognize what the spectator ion is. You're right. Sodium is the spectator ion. Once we do that, balancing this equation will be a little bit simpler, and we can always add the sodium ions back to the balanced equation. But for now, we're just going to keep it in ionic form. So now what you're going to do is go through all of the steps that I just outlined a few moments ago. First step, identify the oxidation numbers. Second step, are you ahead of me? Do you know the next step? Second step, figure out what's oxidized and what's reduced. and beginning writing the half reactions. Balance the atoms first that are oxidized and reduced. Then after you balance the atoms that are reduced, you balance the oxygens with water, you balance the hydrogens with hydrogen ions, and you balance the electrons to make sure charge on both sides is balanced. So pause the podcast, go through that with this example, and on the next slide you'll see the equation at that point. And then we'll talk about what we do if the conditions are basic. This slide shows the oxidation numbers of reactants and products and the determination that the atom of chlorine is what is being reduced and the manganese is being oxidized. The next slide shows the half reactions and the value that each half reaction must be multiplied by in order for the electrons lost and gained to be equal. The next slide shows those equations, those half equations, and now we're going to add them up and cancel some like terms. Now, yes, you're right that the electrons are going to balance out or cancel each other out. And if you'll notice, you see water on both sides. So kind of like adding any algebraic equation, these three waters would cancel out and 4 of the waters would cancel out to leave you with 1 water on the reactant side. If you look at the hydrogen ions, you can see that there are 6 hydrogens on the reactant side in the first equation and 8 on the product side. So these will cancel out and we'll be left with 2 hydrogen ions on the product side. So let's carry everything down now that we're left with. 3 hypochlorite ions plus 1 water molecule plus 2 manganese dioxide molecules yields 3 chloride ions plus 2 permanganate ions plus 2 hydrogen ions. Double check. Look at the total charge on the reactant side. Looks like -3. Total charge on the product side, we've got -3, we've got -2, and we have +2. So net, we've got -3 on both sides. We've got conservation of charge. Now, if you look at this, you'll see that this is done under acidic conditions. Now we're ready to go back and look at the next step that we would do, the final step, if the conditions are basic. According to these directions, and I've tried to simplify them for you, what we're going to do to make the conditions under basic conditions is we're going to add hydroxides to both sides in order to neutralize the hydrogen ions. Now we know what happens then. We'll produce water, and then we'll simplify the waters on both sides. So that's what we're going to do now. So, adding hydroxides to both sides, just like any mathematical equation, what you do to one side, you must do to the other side. I see 2 hydrogen ions on the product side, so I'm going to add 2, not 20, 2 hydroxide ions to both sides of the equation. All right. Now I'm going to, this will form 2 waters, won't it? When it forms 2 waters, you see that I have waters on the reactant side and waters on the product side. Pause the slide, do the accounting, and write the correctly balanced equation before going on to the next slide. Okay, here is what I have. I'm going to double check all of my atoms. Chlorine, total of 3. Oxygen, 3 plus 2, that's 5, plus 4 is 9. I see 9 oxygens on both sides. I see 2 hydrogens. I see 2 manganese on both sides. I see a total charge on the reactant side of -5. I see a total charge on the product side of -5. I've got conservation of atoms, conservation of charge, and the conditions are basic. Problem solved. Now, your task is to take the problems in the packet, the redox problems, and to balance them as best as you can. I'm sure you will find some that are exceedingly challenging. Do the best that you can. Make an attempt on all of them. Watch the podcast a few times to help you with some of the sticking points. Hope this helps. Have a good night.